Okay, so this slide asks the question, why do we want to use PDM, or these pulse density modulation microphones? So the PDM microphone has the microphone cartridge, and inside the microphone there is a high rate, low resolution sigma delta A to D converter. And there's a decimation, outside there's a decimator. So the sigma delta modulator is small and cheap, and it fits inside the tiny little microphone cartridge. The decimator is large, and it requires very large scale integration process, which is already present other places in the hardware. So later on today we're going to be demonstrating this little device. It's about the size of a postage stamp, and it has two of these PDM microphones on this little chip, and each one is maybe 2 millimeters by 3 millimeters in area. And the two of them work together as a stereo pair. So this is really a cheap way to get noise immunity of digital systems. So the analog conversion to digital takes place right inside the microphone cartridge, and the signals coming in and out of the cartridge are all digital. So we can avoid the noise induction that happens with typical analog circuits by being all digital right from the microphone to the device. These are also very inexpensive, so they're very commonly used in smartphones. You'll find there are probably a pair of these PDM microphones. They're also used in laptops and webcams, this sort of thing. Now, PCM is what we were talking about yesterday, pulse code modulation. So in PCM, multi-bit words are handled at a constant rate. And the sample rate, abbreviated F sub s, determines the system bandwidth. And the bandwidth can never be greater than Fs over 2. That's the Nyquist criterion. The word length, or the bit depth, N, determines the signal-to-noise ratio. So we talked about this yesterday and again this morning. So the signal-to-noise ratio is theoretically 6.02 times the bit depth plus 1.76 in decibels. So for 16 bits, you typically get about 94 dB of signal-to-noise ratio. And as we discussed, dither ameliorates the quantization effects. It eliminates harmonic distortion, it eliminates noise modulation. It reduces the signal-to-noise ratio a little bit, but it's worth it because the overall effect on the audio is better. Now this is a classic PCM A to D converter. So you have sharp analog anti-aliasing filter, which is very expensive, it's bulky, and as we discussed yesterday, it'll have poor phase response. So you have a low-pass filter, the signal comes in, the A to D converter, so any of the out-of-band components are filtered out by this very expensive and bulky analog filter, and then we digitize the signal at 48 kilohertz sample rate. There's a precision multi-bit converter. It's difficult to manufacture, it's expensive, and it requires trimming, probably because of the analog anti-aliasing filter. Now the more modern technique of doing this is to use oversampling. So we have a low-pass filter which is not as sharp, not as steep, and therefore less expensive. We would sample at a higher rate, say 4 times the sample rate at which we want to eventually have the signal at. So if we want a 48 kilohertz sample rate, we'll sample at 192 and downsample by a factor of 4. So the requirements for the low-pass filter are reduced. And the digital decimation filter can be arbitrarily close to perfect. That's the advantage of these digital filters over analog filters. You can have linear phase, low noise, a very flat passband, high attenuation, and a very sharp transition between the passband and the stopband. Now, oversampling 1-bit audio, the oversampling or interpolation increases the bandwidth of the system, and it creates extra spectral space, extra space in the frequency domain. But quantization reduces the word length to 1 bit, and this introduces large amounts of quantization noise. So we talked about the increase of the signal-to-noise ratio with the number of bits, and when you only have 1 bit, you get a very high amount of noise. But we can take advantage of a technique called noise shaping, to move most of the quantization noise outside the audio band up to high frequencies where it's not audible. So in PDM, the system that quantizes and noise shapes is called the modulator. So here's an example of 1-bit images in terms of graphics. So this original photograph is a gray tone. It has multiple shades of gray, right? So this would be like similar to a PCM system where you have many, many bits of resolution, and each bit would define a different shade of gray, graduations. Now, if you were to convert this to 1 bit only, the 2 bits are black and white, either on or off, you can say that it's very pixelated and you don't get a very good quality image. But a technique that's used in printing is to use what's called halftone. So you still have a 1-bit system. It's either black dot or white dot, but they vary the intensity by moving the density of the pixels on the image. And you can come up with a system that looks very close to the original grayscale image. So this is a similar concept to how the audio works in PDM. So the quantization error is diffused to the neighbors, correlated noise or distortion is converted to a high-pass noise floor, and we can use interpolation to improve the results. Now in terms of dithered quantization noise, the power spectrum is white. That means it's flat with frequency. And the power is a function only of the quantization step size, or the bit depth. In oversampling systems, some of the noise power is above the audio band, and then it gets filtered out by the digital decimator. So we get a 6 dB improvement in the signal-to-noise ratio for every 4 times higher sample rate that we use. And we need to arrange the quantization noise so that it's high pass. Instead of being flat, we want it to be up in the high end of the audio spectrum. So this illustrates oversampling and noise. Here you have a certain noise power that's in the baseband of the audible band of up to 24 kilohertz. And if we sample it 4 times the rate, we reduce the noise power by 4, and the effect is only 1/4 of the noise power is left in the audio band. So this is an example of the noise shaping that's used in the PDM modulator. So this shows the audio band here from about, well, it's shown from DC actually, but this goes up to about 22 kilohertz here. And as you can see, this is playing a pure tone at 1 kilohertz. That's the big spike in the spectrum. And there's all kinds of noise that's built up at very, very high frequencies. The highest frequency shown here is, that's 1 megahertz, I believe. So what we've done is we've taken the noise from quantization and pushed it out into the spectrum, so it's way up above the audible band. So with these, MEMS stands for micro electronic machined surfaces, I think. These are basically, they're produced out of silicon at the chip level, and there's an electret microphone capsule with the sigma delta modulator built in. So the capsule output is sampled at a high rate. It's typically a 4th order modulator, which is oversampled by a factor of 64, and it has a 48 kilohertz base rate. So an analog delta sigma modulator has cascaded integrators, that's the sigma part of the delta sigma, a 1-bit quantizer, and feedback of the output to the input. That's where the delta comes in. And the order is the number of integrators. So when the PDM is input to a chip or to our analyzer, there's a digital decimation filter that converts from PDM back to PCM. And typically, I2S is used for interchip connectivity. So inside our analyzers, all of the modules communicate over I2S. So APX is a PCM system. To convert PCM to PDM, you increase the sample rate and reduce the word length to 1 bit, and then use noise shaping to push the noise up high into the spectrum. Interpolation increases the sampling rate, and the digital delta sigma modulator reduces to 1 bit. With decimation, we convert directly to analog with a low-pass filter. So for example, the bit clock coming into the system here typically runs at 2 to 3 megahertz. And you can actually take the signal from one of these MEMS microphones and plug it into an analog input. It acts as a low-pass filter, and you get a reasonable approximation of the audio signal. So conversion to PCM requires decimation. This reduces the sampling rate, and it increases the word length at the same time. There's a multi-rate filter structure. CIC and half-band filters are common. We must prevent aliasing into the audio band, so the stop band attenuation must be very high. Actually, something else I wanted to do here, I wanted to point out some resources that we have. And these are items that are available on our website. So this is a PDF document that you can download from our website. It's called the APX PDM Option Technical Details. And this has a lot of information on the general architecture, the transmitter side, the generator, interpolation filter, PDM modulators, overload point. So lots of good information here. It's about 16 pages total. And you're welcome to just go to the website and download that. And then, let's see here. Another resource that we have is Understanding PDM Digital Audio. So this is kind of a white paper by Tom Kite. He's our VP of Engineering and also does all our DSP programming. And just look at the table of contents here. So it's about 9 pages total, and it's got an introduction, some PCM, noise shaping, oversampling, and so on. So that's another good resource. And then finally, I think we have a tech note which you can download called Measuring PDM Microphones and Inputs with APX Audio Analyzers. So this is about 11 pages total, and it covers a lot of good information here that we can look at. Okay. So let's go back to the slide set here. So one of the problems with PDM is overload. Signals that are close to full scale cause the modulator to overload. And unlike PCM, the signal doesn't clip, causing distortion. It just becomes totally unstable. So we can look at this in a loopback mode, but as you increase the generator level up to close to 0 dBFS, it starts to become very unstable. And I think the highest you can go in our analyzer is a generator level of about -6 dBFS. Overload is easily detected at the quantizer input, but excellent performance is achievable. So it's a problem. There are some limitations, and it's different from PCM, which is almost perfectible in principle. So here's some examples of the specifications. For our 5th order modulator, which uses an oversampling ratio of 256, it's possible to get 127 decibels of signal to noise ratio, minus 128 dB of total harmonic distortion plus noise, the dynamic range of 137 dB, and a flatness of 0.0001 dB. That's very flat. The 4th order modulator uses a lower sampling ratio, 64 times, and it typically has 20 dB less performance than the 256 times. But as you can imagine, for one of these little MEMS microphones, you would be looking at a signal-to-noise ratio of about 107 dB. For an acoustic application, that's plenty of dynamic range and signal-to-noise ratio. So let's talk about the PDM module in our analyzer. So the front panel looks like this. It's one module slot wide. There are uses BNC connectors. So there's on the output side, we have the signal, the bit clock, and this connector called VDD. So VDD just supplies the DC voltage to power the device. And on the input side, we have the signal and then the bit clock. So depending on whether you're using the PDM as a generator or as an analyzer, you would connect to the different, the VDD is common to both, but you would connect the signal to either the output or the input, depending on whether the direction of the signal coming in or out. So here's a little diagram here of a microphone cartridge. So you would have one of these PDM microphones, or two actually, and you connect the bit clock to the mic, the signal to the input, and then the VDD to the power source on the microphone. In terms of the output and input settings, we have panels for the output here. This shows the bit clock direction, can be in or out. We have the interpolation oversampling ratio here. This green on black indicator shows the decimated rate and the bit clock rate. And here you have a choice of modulator, I think it's 4th order and 5th order, and then auto oversampling rate. Now the data edge determines how the audio is generated. So in these PDM systems, they're designed to handle 2 microphones as a stereo pair, or sometimes in smartphones they can be used for noise cancellation and echo cancellation. So you can actually, on these PDM pulses, it measures one channel on the rising edge of the pulse and one channel on the falling edge of the pulse. So you can choose how to configure that. We have this scale frequency by value, and then the logic level and the VDD level. So the logic level is the height of the pulses used for logic control, and the VDD level is the level of the DC power applied to the device. And then this button just turns the VDD power on or off. On the input side, we have the bit clock direction, the decimation ratio. Here you would set the decimated rate, and then you would read back the bit clock rate. Same control for the data edge and channels, and then the logic level, VDD, and the VDD on and off. So we provide interpolation ratios from 16 times to 800 times on the output. We provide decimation ratios from 1 time to 800 times on the input. The bit clock direction can be in or out. There's a 4th order modulator or a 5th order modulator. And you can use the rising or falling data edge, or if you want to have stereo with 2 microphones, you can do both. Logic levels from 1.8 to 3.3 volts, and the VDD power from 800 millivolts DC to 3.6 volts DC. We also have the ability to send control codes. So some devices use a PDM input, and you can use control codes, which is a sequence of data to control the device. So on the monitor panel here, there's a provision for sending a monitor code. You would turn it on, choose the direction, MSB first or last, and the edge, and then the value in hex, and the number of times that you want to repeat it. This can also be used as a sequence step in APX. So for automated testing, you can run a sequence of measurements, and you can send control codes as part of the sequence. So here we've added a sequence step called send PDM control code, and really it's just taking the controls here that are available for interactive use and having it run as a sequence step as part of a measurement. In this slide, we're demonstrating sending a series of control codes. So on the monitor panel side for interactive use, you would choose the code as a defined series, and you would specify a table of codes that you can just add additional codes to. This, of course, can also be run as a sequence step as part of the sequencer. And then the third choice is to send indefinitely. So you just choose with this control, send a single code indefinitely. Same controls for the edge and the MSB first. You specify the value and you click the send button. And this will just, I think it'll send as long as the button is depressed. And then for a sequence step, same thing, you add a sequence step that sends codes indefinitely. And there's a similar sequence step to stop sending control codes, PDM control codes, to stop it at whatever part of the sequence you want to. There are some special measurements that are available. They're meant for PDM, but they can also be used for other devices. But in order to use them, you have to have a PDM module inside the analyzer. So there is a power supply rejection measurement. What this does is it applies an AC waveform to the VDD connector, so you can measure the ability of your device to reject AC signals on the DC power supply. So you specify the waveform. One that's very common is a square wave at 217 hertz, and the reason for this is if any of you have ever had certain cell phones that use GSM, if you put it close to an FM radio, you'll hear that chattering noise eventually when a signal comes into your cell phone. And if you look up the GSM system, you'll note that it's related to a 217 hertz square wave. So many times manufacturers want to test their immunity of their devices to that 217 hertz square wave. So here you can set the VDD level, and then you choose the level of the AC signal that you will want to apply to the device. There's also a PSR frequency sweep. So in this case, you specify an AC level, and you provide a sweep table. So in this, as shown in the panel here, we're going to sweep from 20 hertz to 20 kilohertz with 15 steps spaced logarithmically. And that will add a 100 millivolt sine wave to this DC voltage on the VDD and step it through frequency. And you can test the immunity of your device to noise at different frequencies. Then we have a VDD ramp function. So what this will do is ramp that DC voltage used to power the chip from 0 volts up into the, well, from whatever start voltage to the stop voltage that you specify, and you can specify the ramp time in seconds. So as shown here, this will ramp from 0 volts to 3.3 volts with a 100 millisecond ramp time. Another feature that we have available in certain measurements like signal analyzer, you can choose to measure decimated audio. So this is the audio signal that we're looking at. Or you can choose the PDM bit stream. And this has, essentially it's a square wave representation in pulse density modulation at the sample rate of the bit clock. So you would have in the order of 2 to 3 megahertz sample rate, and it shows the bits going all the way up to very high frequency. This shows about 2 megahertz in this graph on the right. This slide shows a little demo fixture that we have, and what you see here is this little chip, and I didn't bring the whole fixture. It's a little bit too much to carry for me. So that's just a plexiglass tube that's about 100 millimeters diameter with a little speaker in the base. But other than that, this chip is the same. So there are, on the back side of this, there are 2 MEMS microphones. You can see the little solder pads on the back of the chip. I think there are 6 pins. And we're just going to do a little demonstration with that. Okay, so just open the analyzer in bench mode, and let's try, let's see, I'll just use no output for now. And on the input side, I will choose PDM. And this will bring up the PDM control panel. So the bit clock direction is out. The default decimation ratio is x64 with a 48 kilohertz sample rate. And you can see that the bit clock rate for that sample rate with 64 times interpolation is 3 megahertz, 3.072 megahertz. So let me turn on the VDD signal, and we should be seeing a signal from that PDM microphone. So you can see the frequency over there. So these are, you know, basically just working like a microphone now. It'll be picking up my voice. And you know, to do acoustic measurements with this, you would require an anechoic chamber or something that's isolated from noise in the system, just like an analog microphone. Typically, you would want to use a reference microphone, like a Grass or Brulin Care analog microphone that's calibrated. You want to set up you know, a loudspeaker to stimulate the device and test it just like you would an analog microphone. Let's see here. We can play around with the sample rate a little bit. So there was a question about, these are the decimation ratios. So let's try going to 128. So here what's happened is that the decimated rate is still 48 kilohertz, but the bit clock rate has gone up to 6.144 megahertz. And then there was a question about the relationship, I think, between the decimation rate and the sample rate. Let's try a different sample rate here. So if I go to 44.1 kilohertz with the same decimation ratio, now my bit clock rate is 2.822 megahertz. And I can go down to 32K, so now the bit clock is 2.048 and so on. So really the bit clock is changing in relation to the decimation ratio and the decimated rate. Let's see how low we can go here. Oh, we can go down to 4 kilohertz is the lowest limit. But these microphones, I think, are meant to operate at a higher limit. So if we're at 4 kilohertz, you know, the bandwidth of our system is going to be less than 2 kilohertz, as you can see here. Let's see if we can still measure a signal. Too high a frequency. I have to whistle at a lower frequency for that. So let's try something like 12K. There you go. The problem with these low sample rates is it takes time to acquire the samples, and the displays don't update as quickly. So the standard rate we'll use here is 48K. And yeah, so once you've configured the system, you can go ahead and do standard audio measurements just like you would on an analog microphone. You can measure the sensitivity, the THD plus N ratio. For an acoustic measurement, it's more common to use THD without the noise because there is so much ambient noise. Now let's look also at, let's see, I could probably demonstrate using this speaker. Maybe not. No, I won't bother. In terms of the output side, what we can do is set the output to PDM, and let's have a look at the control panel here. So the here the bit clock direction is set to in. Let me change it to out. And I choose the interpolation ratio. Let me turn on a loopback connection. So you can see that characteristic dip in the spectrum here. And just to make sure that I'm not contaminating the input, I'm going to unplug my input connector. I'll just unplug all the connectors. Actually, what I'm going to do is I'll pass this around so people can have a look at this little pair of microphones. Those are MEMS microphones made by Knowles Electronics from the United States. And I visited a customer there, and he told me they make billions of them per year. It's really quite a lot. Yeah, so I wanted to turn on VDD. And then let's try generating a signal here. So you can see a very nice clean sine wave, and we're measuring the THD plus N ratio here. If I change it to decibels, so the signal's at minus 20 dBFS, and let's go up to minus 10. So still pretty good distortion. If I go to, let's see, fifth order modulator, you can see my distortion is now minus 116 dB. And you can also vary the oversampling rates. It probably won't do very much. Now one thing I wanted to demonstrate also is, this is the FFT and the scope display. And let's see, somewhere here, is it on this panel? Actually, I think what I'm looking for is in the FFT measurement. I know this works in sequence mode. Yeah, so here, let me close this panel, give us a little more space. So if I choose, let me just measure an FFT. So this is the decimated audio that we're looking at. And if I auto scale the spectrum, it goes up to about 20 to 22K. I can also choose, and I have the scope display here. If I choose to measure the PDM bit stream, you can see, looks quite a bit different here. That, let's see. Yeah, so here the, let me try this, decreasing this to 64. So here the, I'm sampling at a, basically at the bit clock rate of 3 megahertz, and to see something I would have to bring my FFT length up to a much higher resolution. So let's go to 1.2 megasamples. Now to take 1.2 megasamples at a low frequency like 48K, your acquisition time will be very long. But at this clock rate, it will not be very long. It's very fast. So you can see some of the noise shaping going on here in the background. And if we look at the scope display, and if I just zoom in here, keep zooming in, whoops. Eventually you will see the bit patterns. Let me just go properties. So let's look at from 0 to 1 microsecond. Oh, that was the... yeah, so we're looking at the PDM bit stream here, and you can see the actual pulses in the bit stream. So I've got the 2 channels. If I turn one of the channels off, you can see. So that's the actual bit stream coming in. And one of the nice features of the analyzer here is you could, for example, set the acquisition length. Instead of using auto, you could set it to a certain number of seconds, acquire the signal, and then by clicking this export button, you could export the bitstream data to a file, such as a MATLAB file or a CSV file, and process it any way that you like. Okay. Now we could look at the, in sequence mode, some of the other PDM measurements that we have. So let me choose non-external. Yeah, for testing a PDM microphone, I would be probably driving a loudspeaker and measuring the response acoustically over PDM. Let's go to PDM here. I'll turn on the monitors. And then, let's see. Oh, and I unplugged my device, so it's wandering around the floor there. So I was going to connect the microphone, but I can't do that. Okay, so while that's traveling around, I can show some of the measurements that we have here that are available. So there's the PSR measurement, PSR frequency sweep, and VDD ramp. So the PSR measurement will just, I guess I could maybe do this in loopback if I switch to PDM out and then loopback. Now I should be able to just generate a signal. There we go. So let me go back to that measurement. And so here we're generating a VDD level of 1.5 volts and an AC level of 100 millivolts peak to peak. And if we turn on the generator, so this is measuring the immunity of the system to that signal. So we have results, power supply rejection, which is shown in dBFS, power supply rejection plus noise, PSRR, and this requires an analog input. So in this case, you would be testing a device. Yeah. This would be for something like an analog MEMS microphone, which is not PDM. It has an analog output. This is the PSR frequency sweep measurement. So as I showed in the slide, you can just set the start and stop frequency. And let's just go ahead and try that. So this is sweeping the frequency over 15 points logarithmically, and this will measure the power supply rejection as a function of frequency. And then we have the VDD ramp, and this is showing the instantaneous level on the input versus time. So this is going to ramp from 0 to 3.3 volts with 100 millisecond time. Let's just see what that looks like. Yeah, so this was 100 millisecond ramp time. Not really going to see anything in this case. You would have to have a signal connected. So the use case here is if you wanted to see, as you increase the VDD power level, you want to see when the system turns on and starts measuring audio. So you could do that here. Let's see, there's a so there's a PDM panel here where we can send codes, and you have a choice of defined series or a single code indefinitely. And then also on any of the measurements, you can add a sequence step by right-clicking on the measurement and selecting Edit Prompts and Properties. And if we look at the steps available here, there's a step to send a PDM control code, and also a step to stop sending a code. So you could do that as part of a sequence.